At the next stage, we are going to calculate the nominal voltage range of the motor at dropped voltage condition and high voltage condition, since voltage can be fluctuated at any time depending on the distance between your destination and the nearest distributing transformer, also due to the variation of frequency. Hence, I thought to make this motor capable to work between 120 V and 250 V without any effect. Thus, the nominal current of the thermal overload cutout I'm going to use to trigger at, with respect to time, should be decided. Therefore, another calculation has to be done. Finding the most relevant thermal overload cutout for the protection of motor to avoid being the motor burnt due to overcurrent flow is important. Since, as I noted my objective is to run this motor at the rated current of 4 amps, and hence, I don't like to bring my efficiency down while letting the motor to run at a higher current flow, especially more than 4.5 amps. But due to the voltage fluctuating, the current can be varied, and hence I'm trying to make this motor capable to run between 120 volts and 250 volts. But I want to keep my efficiency at a constant range. Power required at the output equals voltage times current times power factor, where the required power output always is 0.75 horsepower equals 746 watts and power factor is 0.95. Now, in this calculation, we have found that the maximum current is going to be 6.5 amps and it is at the 120 volts condition. Hence, now I'm going to select a necessary thermal overload cutout to break the running motor circuit at or above 6.5 amps, taking 6.5 amps as the nominal level. Hence, after choosing a particular brand supplying TOCs for industrial motors, the nearest values are as follows with respect to the time. For example, it will trip at the current given under actual tripping current, but after it's been running for 16.6 minutes and all the currents above the given tripping current will be cut out in a less time than 16.6 minutes. Therefore, I thought to select the B37U, which is going to be cut out at actually 7.1 amps after a 16.6 minutes run. Hence the TOC is as shown here. Now I'm happy to inform you that all the electrical findings we have now been determined, and from now onwards we are able to step into the physical construction phase of the motor. Remember, at the start, you had nothing on your hand, but you are done successfully designing the required motor scientifically. Please note that this is highly important. When the gap or the space between the inner surface of the stator and outer surface of the rotor increases, the efficiency of the motor decreases and hence the current increases, leading to higher power loss. Before going to step up to that, I have at the beginning told you all that as the second part of this long journey, I'll show you the software implementation or simulating the designed motor for better verification. So, I hope you are cleared in this part and we'll step into our simulation phase then. Don't forget to subscribe to our channel also. If have not yet been subscribed, please subscribe. For simulating our mathematically built design, you will need the following software, and herewith for your convenience, I'll drop you a link to a video on our channel in the below description where you can visit our software storage online and download the full version of ANSYS and Softmax well free. Accept this as a gift from me for your interest in learning and staying tuned with us further. See you on our part 2.